Good morning, afternoon, evening, everyone, depending on where you are. Uh, I am Shashank Shekhar, and I am founder of AI Ordinate. We are, a startup building an LLM ops platform focused on reducing cost and latency and enhance, the quality of LLM applications and systems. Now, what we're also doing, is putting significant focus on enhancing, the security of large language models, right? And our efforts involve addressing, key aspects to ensure the robustness and safety of, the large language models in various applications and environments. uh, I have more than 16 years of experience in artificial intelligence, machine learning, deep learning, right? And I have worked in multiple large tech companies, including Amazon, VMware, Flipkart, Target, among others, right? Today, as Conrad said, right, the topic of my presentation is LLMs beyond the hype, right? A practical journey to scale. Now, the world of LLMs, has grown a lot, right? In last 1 year, right? 1 year or so, right? And it has given us, many choices for creating and analyzing text, right? But using these powerful models can turn out to be very very costly, right? And in my talk today, I will carefully look at ways to find a good balance, making LLM systems cheaper, also making them work better. That is, improving quality and also making them faster, right? So decreasing the latency. Now, what I will also do is delve into the anatomy of LLM-based applications, and we'll talk about some practical strategies of deploying, large language models at scale. So, if you see the slide, right, the reference architecture of LLM applications, right, has begun emerging in last few months, right? If you see, there has been a lot of work around this, and the components leveraged in a particular LLM application is, function of course, the use case, right? The requirements, and also, the user preference, right? And broadly, these are the six key components of a generic LLM application, right? Now, the first one, of course, is choosing the right large language model, and it is very important, right? Because there are a lot of considerations around it, right? There are a lot of factors around it. Now, one key factor is, of course, the size of the model, right? That how many parameters have been used to build that model, right? Typically, if you see, typically larger models will give you better performance, but in recent times there has been advent of quite a few smaller models which perform better than their larger counterparts, right? And since cost and latency are other important parameters to consider while choosing a model, you know usually smaller models uh, are cheaper and faster, and hence, right, if you have a smaller model which performs at par or slightly below par a larger model, choosing the smaller model is the right thing to do, right? Is more prudent given the trade-offs, right? The next crucial parameter, right, while choosing a large language model is, of course, the licensing, right? There are, of course, quite a few open source model, and there are quite a few behind an API, right? So if the intent is to develop a commercial application, it is important that you ensure that the model that you use has an API licensed for commercial use, right? Um, and one key consideration is that while some LLMs may have tokenizers and embedding models built within, some others will require you to run these steps yourself, right? So also, one more thing, right? Before you customize your LLM using techniques like fine tuning, or in context learning, or RLHF, right? It is important to check how well and quickly and consistently the model generates, your desired output, right? And this is something which you should check before selecting, the large language model of choice, right? And how you do that, right? How you measure the model performance, right? Of course, you'll have to do offline evaluations, and what is offline evaluations? That offline evaluations are set of tests to measure model performance before, interacting with human, right? So they do typical measurements, right? Like latency, accuracy, and also, contextual relevance of a model's output, right? And how it does is that it asks the questions, right, to the model, and then you have either correct or incorrect answer, and based on that it evaluates the model performance, right? Now, in case there are not, ones, or there are no ones or zeros, so there is no correct, incorrect, but ambiguous answers, there is a subset of test called incremental scoring, right? So what you can do is score a model's output incrementally correct rather than, 100% correct or incorrect, answers. um, so the second component is, of course, prompt template, right? And pretty popular, right? I mean, prompt engineering has evolved as a core activity in LLM application development, right? There are several prompting techniques, right? Including, zero shot, few shot, chain of thoughts, among others, right? And they are being leveraged widely. For making the whole system work better, right? Now the third component, and is very important one, is the vector database, right? And of course, with the popularity of large language models, vector database has also become quite popular in recent, time, right? Now, where vector databases help is with retrieval augmented generation, RAG, right? Which is, I mean, if you put it simplistically, right, RAG is nothing but what it does is that, the relevant external information is first chunked into, blocks, and by block I mean, sentences or paragraphs, and then tokenized, right, and then run through an embedding model. And these are then fed into a vector database, right? So RAG is needed for use case which require access to information that the large language model, or the large language model that we have chosen, has not been trained on, right? So and additionally, the prompts are also vectorized, right? And what happens that once the prompts are vectorized, similarity search is performed to retrieve, relevant entries from the database, right? And these entries are then fed, alongside the original prompt, providing context needed to provide a much coherent response, right? Now, one thing I want to mention here is that, this thing also aids in AI trust, right? And how it does is that the large language model may cite which chunk it has used in its response to counteract, potential hallucinations, right? So and that's where vector database also plays an important role. Now there are quite a few popular vector databases, right? Pinecone, Chroma, Qdrant, right? And of course open source vector database is also there, right? PG vector, right? The next component are the LLM agents, or you can say LLM agents and tools, and they are needed to perform actions beyond text generation. Typically, LLM, if you use alone, right, you can only do text generation. So just limiting the usage to LLMs, makes the application quite constrained, right? And hence, agents, play an important role. I mean, they can do tasks like web search, maths calculation, database lookup, and others, right? Now, with agents, there are, quite a few frameworks that have also evolved, and the idea of, you know combining reasoning, right, alongside taking action using tools has led to emergence of a very popular framework called React, right? So what React does is an iterative process, right? It basically enters a loop of thinking which action to take, right? And it then takes that action, observes the result, and then decides on the subsequent action to take, right? And it does this in an iterative fashion till the solution is found, right? Now, this approach, of course, React framework and the approach associated, has been found to be outperforming baseline LLMs for sure, right? But one of the key challenge with this is the performing, or basically performing the evaluation or evaluating, the performance of these systems, because it's pretty challenging, right? So that's one key challenge. I'll touch upon that in a subsequent slide on this, right? Now, the other major component is, of course, the orchestrator, right? And you can have orchestrator because it helps you create abstraction on top of the language model, the prompt template, data sources, agents, and tools, right? And of course, LangChain and Llama Index are quite popular, and everyone knows, everyone know about that, right? Now, one component that I have missed here is, of course, LLM cache. I think LLM cache is important component for throughput improvement and cost optimization, and I will touch upon that in a subsequent slide. Here I have missed that, right? And of course, the last major component is the monitoring module, and as is the case with any ops engine or application, monitoring key metrics like performance, latency, throughput, CPU, GPU, memory usage, right? Drift, potential drift, right? All of these are very, very important. Now, what you can do is that you can develop your own monitoring module, right? Leveraging open source tools like Grafana. But there are, some tools which gives you out of box monitoring capabilities, right? Langsmith is one. The most popular one, of course, is Seldon Core V2, right? Because with Seldon Core V2, you can also detect potential bias, and it has also got some explainable AI measures, right? Um, and then therefore, I think monitoring falls under the purview of AI trust or responsible AI. Now, in this slide, right, this I picked up from one of the popular GitHub blog, right? Now, this is a visualization depicting the anatomy of typical LLM application, right? Now, if you look at this, the components needed to build your LLM app can be, roughly be clubbed into three categories, right? If you see, the first category, right, is that of user, interface, right? Or basically, user UI or LLM host, right? So if you see here, uh, the user input is the requires a UI, and here is the UI, and then you have an LLM API or LLM and app hosting platform. So the UI and LLM app hosting platform can be in the category of user input, right? The second category can be input enrichment and prompt optimization or prompt construction tool, right? And here you will have your data source, of course, right? And embedding model, right? And a vector database, right? And of course, the prompt construction optimization tools, right? And the data filter. The last category is, as I said earlier, is of responsible AI tooling, or I would call it efficient and responsible AI tooling, and that includes the cache, so the LLM cache, and the LLM content classifier, and the telemetry. Right? So these are three rough categories. Now let's look at each block in this diagram. Now LLM API and host, right? So this particular block. So as far as LLM app is concerned, right, this that can be hosted on-prem as well as on cloud, right? On-prem hosting is much more cost effective, but of course requires some deep expertise to do it end to end, right? The UI, here serves twin purpose, right? It is leveraged by the end user to send, query um, um, to the LLM, and also acts as a consumption layer, where you can retrieve the responses for a given query, right? The vector database, we already talked about it, is the one where you can store embeddings, and then the data filter is to ensure that LLM isn't processing any unauthorized data, right? The prompt optimization tool, helps prioritize, which content embeddings are most relevant, and also in which order those embeddings should be organized, right? To ensure that the LLM produces the most contextually relevant response. LLM cache, which I said is very important, basically stores all the responses. I mean, if you simplify it, it basically stores all the responses, and this is essential to improve the throughput, latency, and cost. Because if similar queries are being asked, that doesn't hit the API, but sends response from the cache, right? So that's where you can optimize for cost as well as latency. The content classifier, right, or a filter, right, content filter prevents the system from responding, offensive or harmful content, right? And lastly, as I said, telemetry, right, evaluates the efficacy of the app and how well it is working with the actual users. You can have bunch of monitoring modules in telemetry service. Now, in this slide, I want to talk about 7 key patterns of efficacious LLM system application, right? The first one is, of course, evaluations, and they are a set of measurements used to assess a model's performance on a task, right? They include, benchmark data and metrics. Now, one of the key challenge, of evaluating large language models is that they often produce open-ended outputs, right? So there's nothing like a ground truth to compare it, right? So for example, if you've generated an essay, or let's say you've generated an email leveraging an LLM, how you'll measure the quality? I mean, there's no way you can measure the quality because there's no ground truth, right? Now, one potential way, and which is also being leveraged across different areas, is having human annotators to evaluate the quality, right? But this could become very, very subjective, right? Because not only subjective, but it's also very noisy, and also it can turn out to be very slow and expensive affair, because you cannot have human evaluating each and every output that comes out of elements, or a portion of output that's coming out of an LLM system. So while it is a good method, it might not be very. It's not very good. I mean, it's subjective and noisy, but in some cases, it might turn out to be good method, but it's not very efficient method, right? Now, one potential way is to benchmark against the best available individual LLM, right? So you see in today's world, GPT-4. Just using a rule of thumb, which is not 100% correct, but if you say that a model with maximum parameters, is the best individual LLM. I mean, GPT-4 wins the race. So you can, leverage GPT-4 for benchmarking and evaluation, right? Now, the next one is, of course, RAG, and as I already mentioned, it is a technique that combines, LLMs with, document retrieval to generate outputs that incorporate recent and external knowledge, right? Now, RAGs work by first, retrieving relevant documents from a large corpus based on the input query or context, and then feeding the retrieved documents as additional context to the LLM generation, right? Now, there are several ways in which RAG can be done better, right? I mean, of course, there is using the right embeddings for the right problems. You can also you know do quantization, right, using scalar or binary quantization on your vector store, right, to improve the latency and throughput on your vector store. But for that, your vector store should support such quantization, and then re-ranking, also a way to improve RAG significantly. Fine tuning, right, is the process of taking a pre-trained model and further defining it on a specific task, and to get better at a specific task, and that's also a method. Casing I already discussed, right? It's essential for reducing latency and cost. Guardrails, are set of rules or constraints that ensure that quality is of good quality and is reliable, right? So what it does is that it prevents error and failures, and also enforce standards and expectations, right? And defensive UX, right, is more of a design principle, right, that anticipates and manages any adversarial events while you are interacting, while a user interaction is happening, right? So things like hallucinations, inaccuracies can be anticipated and then kind of mitigated or managed, right? So these are basically set of guidelines for human AI interaction that can happen across the user journey, right? So it can be before the interaction happens, during the interaction, when something goes wrong, as well as over time, right? And the last pattern is, of course, collecting user feedback, and very essential, right? Because this is essential for learning the preferences of user and contributes to building the evaluation mechanism, the evaluation, the fine tuning, the guardrails, right? And it also helps us improve our models by learning what users like, dislike, and their preferences. Now, this is the graph depicting LLM patterns across the axis of data to user and defensive to offensive, right? Now, if you see here, um, fine tuning and retrieval augmented generation, which are generators, are high on improving performance. So if you want to improve performance, you can do these, right? Whereas caching and guardrails, or basically collecting user feedback and defensive UX, are high on user experience, right? Or overall user engagement. Casing and guardrails are mediators, right? And they are kind of they kind of help you reduce the cost significantly. And then evaluation is necessary to ensure that your output, your performance of the system is optimal, right? And data flywheel is the process of continuous data collection and help improve the model, and leads to better user experience. And that's where you have data flywheel very well as well. Now, you know if you see, let me quickly discuss some of the key challenges with LLM deployment, especially in an enterprise setup. Right now, accuracy and quality of output is a key challenge, right? Especially when you have varied context and large number of use cases. Generalist models tend to achieve lower accuracy on a specialist task, right? So accuracy is definitely a key challenge. The second challenge is that of cost, right? As I said, the best individual LLM, let's say GPT-4 is quite costly, and there are the other cloud-based models are also costly, and enterprise find it difficult to justify ROI through if they do the cost benefit analysis currently on the LLM models that are available, right? Now, latency is another big challenge, right? And can affect the user experience as well as efficacy of LLM system, right? The other key challenges, right, are of course scaling prompt engineering, because that is handling ambiguous output format, inconsistency in user experience, right, and optimization pattern, right, that is prompting versus fine tuning. Now, here, what I'm doing is I'm recommending an approach, and this is inspired by Frugal GPT, but there are a few additional elements to it, right? For deploying, large language models at scale, right, with lower cost, higher quality, right, and reduced latency. Now, most current deployments leverage, an individual LLM, so one LLM, right, and then a bunch of things are done on top of it, right? Now, the recommended approach basically entails, right, leveraging multiple LLMs, right, along with bunch of techniques which are, kind of acronym here as PSA, LLMA, RHUF, and LLMC, along with, prompting techniques, right, to achieve, substantial efficacy or efficiency gains, I would say, right? Now, PSA, as you see in the last slide, refers to prompt selection and adaptation, and basically involves identifying and selecting effective, when I say effective, often shorter prompts to save cost, right? Some of the techniques within, PSA are prompt shortening, selecting most effective and shortest prompt, as I said earlier, right? Deduplicating the queries, right? Or prompts based on similarity. So not I mean, based on some similarity score, and then query can concatenation, right, to aggregate multiple queries to share prompts. LLMA refers to LLM approximation, and what it does is that it aims to create simpler and cheaper LLM that can match the performance of a more powerful, right, but expensive, model out there, right? Now, in practical terms, right, this could involve choosing a less expensive model that has been shown to perform well on a particular type of task, right? Um, and then um, you know, uh, so for example, and then basically, you are you can also do, completion caching, right? Completion caching is nothing but the caching that I talked about, right? Model fine tuning and model evaluations are also within LLM approximation. And then RHUF is request hedging basis user feedback, and this is very important. I mean, this is a technique which initiates. So in this technique, what happens is that the streaming response, right, is initiated using the fastest model, right? And then what you do is you edit the output on the UI when a better but a slower model response, right? Now, request hedging can also be done, not only based on the response speed, or based on latency, but to save cost by leveraging user feedback, right? So if a user is happy, right, with the output of a faster, a smaller model, you can send a smaller portion of your request to the best individual LLM, right? And more requests can be sent to the smaller model, right? And this also improves, this will also improve, or this will help you improve the quality of your system over time, because what you can do is that you can do your evaluation of your responses to user, right, leveraging best individual LLM, because you are still sending some portion of your request to the best individual LLM. LLM cascading, right, is a popular concept because of Frugal GPT. And what it does is that it basically focuses on, adaptively choosing which large language models to use for different queries, right? Now, in practical terms, this could mean using a less expensive model for simpler queries and reserving the more expensive models for more complex queries, right? Now, what you are doing by doing this is you are only paying for the more expensive resources when you really need them, right? Now, in this module, there is a linear regression-based scoring function generator, which generates a reliability score given a query and a response, right? And there is a LLM router which routes the query to a particular LLM to optimize for cost, latency, and quality. Now, in interest of time, I'll just run through it fast. When it comes to optimizing resources and cost, right, LLM compression techniques, right, are of utmost importance, right? I will not go into each of these, right? Now, when it comes to model compression techniques, right, they are critical to shrink the LLMs, making them viable, right, for low resources devices, and reducing, of course, their uh, um, cost and also environmental footprint, right? Now, here's a taxonomy of different compression methods, right? There is pruning, knowledge distillation, low rank factorization, and quantization. Now, in the interest of time, I will not go through each of these, but I will quickly discuss quantization, as it is the most important compression technique and it is vital for on-prem LLMs. Now, the most effective way for saving long-term cost is to have on-prem LLMs. Now, if you see here, a simple quantization helps compress a large model, right? Large language model like Llama 2, right? 7 billion, 13 billion, 70 billion parameters. We're almost 3 to 4x. So 128 GB original size FP16 model, leveraging, llama.cpp quantization method, has decreased the size to 40.7 GB. And it's very important method. See, one of the ways to decrease the cost on longer term is, of course, leveraging on-prem LLMs, right? And for that, I think quantization is very much important. You can do quantization for enabling inference on CPU as well. So if you see GGML, right, llamas.cpp is one part of one way of GGML, right, is the way to do quantization for inference on CPU. And these are different methods of quantization. So I think pretty much that we are at over the hour, but very happy to answer any question that you might have. Thank you.